All right, we're going to continue our discussion in chapter 6, exponential and logarithmic equation and inequalities. We covered some of the properties of logarithm. Please make sure to list all those up to refer to. You need to memorize those. We're going to review some of those again. But for today, for b greater than 0 and a is not equal to 1, b to the power of x is equal to b to the power of y if and only if x is equal to y. So this would be a case where we can make the base the same and then conclude from that the exponents would be the same to solve equations. If x is greater than 0 and y is greater than 0, then log of x is equal to log of b. Then log of x is equal to log of y with the base b, if and only if x is equal to y. So if I have log of x equal to log of y, if they have the same base, we can conclude from there that x must be equal to y. We can conclude that the argument must be equal to each other. We're going to use all these properties to solve equations. Type 1 exponential equations solved in previous sections, if you recall. We can easily solve this type of problem where we can make the base the same. We looked at some examples like 125 to the power of x equal to 5x. Because I can make the base the same, I could easily solve for x. For the second type of the exponential equation, where we cannot make the base the same, for example, if I have 7 to the power of x equal to 12, I cannot make 7 and 12 equal each other. So in this type of problem, we're going to take a log of both sides to solve for them. Let's take a look at this example. Solve 7 to the power of x is equal to 12. We cannot make the base the same. So what we do in this case is we take a natural log of both sides. We could take a log of both sides also, by the way. If I take a natural log of both sides, on the left-hand side, I get natural log of 7 to the power of x is equal to natural log of 12. Now, natural log of 12 is a number, which you can enter in your calculator. You get, this is a constant. If you recall, we had a property from last time. If I have natural log of x to the power of n, I can move this n right front of the log or natural log, and we call that as one of the properties power rule, where we can take these exponents, put it right front of natural log or log. This also would be true with log. If I have log of x to the power of n, I can move the n right front of log and write it as this. So that's what we're really doing here. We are moving this x right front of natural log so I can isolate x. That's what we're solving for. So my coefficient of x would be natural log of 7, which is another constant. If I divide both sides by the coefficient of x, which is natural log of 7, then you can find x equal to about 1.277 just by entering these values in your calculator. The exact solution is natural log of 12 or natural log of 7 or log of 12 or log of 7. And the approximate solution would be about 1.277. We can easily verify these results by using your graphing calculator to graph both functions and then see where they intercept. And as you can see, the values would be very close to what we calculated. Solve 7x minus, solve 7 to the power of x less than 12. If you go back to your graph of the calculator, because the graph of 7 to the power of x is below the graph of y2 is equal to 12 for all x values less than. So the solution would be all the number from negative infinity to this value, which is 1.277. Going back to the graph, you can see all the number from negative infinity to this number. So Greater than would be from this point all the way to the positive infinity. So this would be really is 7x minus 12 greater than 0. And then if you recall looking at your graph on your graphing calculator, all the numbers from that point of intersection was 1.277 to infinity would be above or greater than 0. This example here also is the type that we cannot make the base the same. We have 2 on the left-hand side and 3 on the right-hand side. We cannot make 2 is equal to 3. So in this example, you would take a log of both sides. And when you do that, again, we're going to use that power rule. If I have log of x to the power of n, that is the same as n log of x. You want to write this down somewhere as one of those properties that you want to remember. So this exponent, 3x plus 1 and also 4 minus x, would go right front of this log for both of them. So on the left-hand side, I would get 3x plus 1 times log of 2 equal to, my exponent here is 4 minus x times log of 3. You remember we're solving for x. So I need to distribute log of 2, distribute log of 3 from both sides of the equation, and look for the terms that contains x in it. So I have this term, I have x. This terms, I have x. I need to move all these two terms that contains x in one side of the equation so I can factor the x out. And the other values of log of 2 and 4 log of 3, these are just the constants. We can use our calculator to find its value. So in this case, I'm going to move all the terms that contains x to the left side of the equation by adding x log of 3 to both sides of the equation. And then I'm going to subtract log of 2 from both sides of the equation. So these two are constant again. And here I have x and x. I need to factor the x out so I can solve for x. If I factor the x out, I get x times 3 log of 2 plus log of 3. And this would be my coefficient of x now. So if I divide both sides by coefficient of x, this would be my x. Now, all these terms are just a number. We can use our calculator to evaluate that. And you get something close to 1.165. Now would be a good time to pause the session, see if you can actually get these answers using your calculator. In this example here, we have log of x plus 6 minus log of x plus 2 on the left-hand side. On the right-hand side, we have log of x. We need to recall a few properties that we learned before. One of them is if I have log of x minus log of y, that would be the same as if I were going to combine this, that would be log of x over y. So if you have a quotient, you expand it as the difference, if you recall. And we had another property where log of x is equal to log of y. We can conclude from here that x must be equal to y. So these are the two properties that we're going to use for this equation. You notice that I didn't bother with the base. If I don't put any base, it means it's 10. But the base has to be the same if it's not 10. So you have to indicate what it is. So in this case, the base is 3 for all of them. So I'm going to go ahead and combine these two using the first property here. So that would be log of x plus 6 over x plus 2. This would be log of x minus log of y. So we can write it as the quotient. And keep in mind that x plus 2 has to be greater than 0. Also, x plus 6 must be greater than 0. So x must be greater than 0. All the number from 0 to infinity is what our solution going to be lie on. So in this case, if I use the second property, if log of something is equal to log of something else with the same base, the argument must be exactly the same. So the argument on the left-hand side, which would be x plus 6 over x plus 2, must be equal to x. So I drop the log by using those properties. Now this is just an equation that I can cross multiply and solve for. I get x plus 6 equal to x times x plus 2, but you should know how to solve a linear equation by now. So this turns out to be a second order equation when you distribute, and we get into standard form. Once you get into standard form at this point, you can either factor it or use quadratic formula. This is factorable, so I can solve for x being x equal to -3, x equal to 2. X equal to -3 is not going to be within the domain that we indicated. We said it has to be positive, greater than 0, so we're not going to include x is equal to -3 as one of our solution. So the only solution we have is x equal to 2. We can use brackets to show the solution. We can use our graphing calculator to obtain the same results. If I enter this equation y1, which is log of x plus 6 with the base 3 minus log of x plus 2 with the base 3. And then on the right-hand side, if you recall, we had y2 would be log of x with the base 3. If you show that on your calculator, you would see the point of intersections. You can see where these two graphs intercept, and that would confirm the result that we use by hand. Let's take a look at this example here. Log of 3x plus 2 plus log of x minus 1 equal to 1. We're going to recall some of the properties we learned before. If I have log of x plus log of y, that is the same as log of x times y. So if the argument is a product of two terms, we can expand it as sum of log of those arguments. So in this case, if I look at on the left-hand side, I can write this as log of 3x plus 2 or times x minus 1 is equal to 1. So on the left-hand side, as you can see, you can combine this into one single logarithm. And once you get it to this point, because the right-hand side is not log of something, so I can go back to my other property that we had before. If I have log of x is equal to y with the base b, I can write this as its exponential function. The base of the log, which matches the base of the exponential, so b to the power of y is equal to the argument x. This is another one that you need to remember. So over here, my base is 10 because there's no number here. So if I want to write this as its exponential function, I will write 10 to the power of 1 is equal to my argument, like we have here. So here is log of, my base is 10. My argument here is the product of these two binomial, and my y here is 1. So if I want to use this formula, I would get 10 to the power of 1, b to the power of y is equal to the argument x. This is my x. As you can see, we have 3x plus 2 times x minus 1 is equal to 10. Now we drop the log, and I can solve this equation by distributing. I get the second order equation. At this point, if I can factor this, I factored. If not, I can use quadratic formula. Looks like this is not factorable, so I'm going to use the quadratic formula to solve for x. You get two solutions. You want to keep the positive one, not the negative one. The one with minus square root of 145, 1 minus square root of 145 over 6, that results into a negative number, which is less than 1. And it is not the one in the domain. It has to be positive. So we're going to reject this one, and the only solution would be 1 plus the square root of 145 over 6. This is a number. We can input the values in your calculator and find the approximate value of this. And as you can see, you can find the result using your graphing calculator, and you can see the result would be very close to what we calculated here. Same problem here. If f of x is equal to 0, when f of x is less than 0 or greater than 0, and f of x is given to me as 3 log of 2x with the base 2 minus 15. For first part, I have 3 log of 2x minus 15 is equal to 0. I can isolate the log and divide both sides here by 3. Then I get log of 2x to the base 2 is equal to 5. Now, in order to solve for this, because in the right-hand side, I don't have a log of something, I need to rewrite this as its exponential form. So it would be 2 to the power of 5 is equal to 2x. 2 to the power of 5 is equal to the argument 2x. Again, you need to know this property. If I have log of x is equal to y with the base b, I can write this as an exponential function, which is base b to the power of y is equal to the argument x. You need to memorize that. So once we do that, we drop the log, we can solve for x. X would be equal to 16. So the solution would be 16. Now, if you look at the graph of this function, you can see right at the point 16 is where would be my solution. If you want to find the values that is greater than 0, would be all the number from 16 to infinity. And if you want to find the values that are less than 0, you look at the graph that go below 0, would be the values that from 0 to 16. Not including 0, that's why we're going to use this parentheses. Not including 16, that would be the values go below 0. So 16 to infinity would be when y1 is greater than 0, for x equal to greater than 0. Therefore, the solution set would be all the numbers from 16 to infinity. Let's take a look at this example. E to the power of minus 2 natural log of x is equal to 1 over 16. There are some properties that you can recall for this one as well. The first property is right here. If I have minus 2 natural log of x, if you recall, I can move this number here, put it right on exponents like that. That's what we're doing here. So again, if I have log or natural log of x to the power of n, I can write this as n natural log of x. That's the property we're going to use to move this negative to right on the exponents here. Now, if you recall this next property, if I have e natural log of x, this whole thing would be equal to x. So if you have or if I had natural log of e to the power of x, both way would be equal to x. We did have similar property for log. If I had log of x to the power of n, if my base is matching here, then the whole thing would be equal to n. We had another one, the combination of that. When I had e log of b to the power of x with the same base b, that also would be equal to x. So these are really handy properties that you need to recall. So over here, as you can see, e and natural log would be like this one, that the whole thing would be equal to x, which is x to the power of minus 2. So at this point, we're going to drop in all the natural log. You should know how to solve for this. This would be x to the power of minus 2 is equal to 1 over 16. I can make the exponents the same because 16 would be really is 16 to the power of minus 1, and 16 is 4 times 4, which is 4 squared. So on the right hand side, 1 over 16 is the same as 16 to the power of minus 1, which is equal to 4 squared to the power of minus 1, which is equal to 4 to the power of minus 2. That's how you can make the exponents the same. So conclude from there that the base must be the same. So x would be equal to 4 in this case. And that would matches the result we got using our calculator. Let's take a look at this example here. Natural log of e to the power of natural log of x minus natural log of x minus 3 is equal to natural log of 2. We're going to recall some of the properties on the left-hand side. We said if I have natural log of e to the power of x, because the base here is e, these are matching, so this whole thing would be equal to x. That's the first property we're going to use to write this here as e to the power of natural log of x to just x. This would be just x. This would be the same as saying e to the power of natural log of x is equal to x. Either way would work because the base here is e. All right, here I can combine these. The property that we recall is natural log of x minus natural log of y is equal to natural log of x over y, just like we did with the log. So I can combine these into writing as a quotient of the arguments would be natural log of x over x minus 3. Now from here, if I have natural log of x is equal to natural log of y, I can conclude from here that x must be equal to y. And that's what we're doing here. We are saying that the argument must be the same. Then you can cross multiply and solve for x. X would be equal to 6. Let's take a look at this example. We have e to the power of 2x minus 4, e to the power of x plus 3 is equal to 0. We can use substitution method for this one. If you recall, if these two terms are square of one another, we can make the substitution. So in this case, I can let e to the power of x be equal to another variable w or u. So if I square both sides, then u squared then would be equal to e to the power of 2x. So everywhere I see e to the power of 2x, I'm going to substitute that with u squared, like here. Everywhere I see e to the power of x, I'm going to substitute that with u. So I'm forcing this to be a second order equation. And I know how to solve this by factoring this. I get x, u is equal to 1 and u is equal to 3. If u is equal to 1, I have to go back to my original assumption. I said u is equal to e to the power of x. Still solving for x. So e to the power of x would be equal to 1, and also e to the power of x would be equal to 3. I have to solve these two equations for x. To do that, I need to take a natural log of both sides. And I take a natural log of left-hand side and natural log of right-hand side. This would give me just x. Remember, natural log of e to the power of x is just x because it's a base is e. So on the left-hand side, we just x. On the right-hand side, we get natural log of 1. And we know natural log of 1 is equal to 0. You can use your calculator or use the properties that we learned. So natural log of 1, here is e. The base is e, equal to a number we don't know. Let's say we don't know what that is. So if I write this, that would be e to the power of x is equal to 1. If I write as exponential, okay. So what's exponents should be in order to get 1? Any number to the power of 0 is equal to 1. So therefore, from here we conclude x must be equal to 0. That's how you can calculate this, actually, or you can use your calculator. And in the case where e to the power of x is equal to 3, again, we take a natural log of both sides. We get natural log of e to the power of x equal to natural log of 3. Again, on the left-hand side, we get x is equal to natural log of 3. Natural log of 3 is just the constant. You can use your calculator to evaluate that. So the value would check out. One solution would be 0, and the other solution would be natural log of 3. We can confirm our result by using our graphing calculator. And as you can see, the graph going to intercept at these 2 points that we calculated. So this would be a summary of what we talked about with those examples. You may want to pause the session and look at these methods that we reviewed. For the first one, we're saying that if I have a to the power of f of x equal to b, and when you're trying to solve for x, the method is to take a log of both sides. The second case, if I have log of f of x equal to log of g of x, we can conclude from there that f of x must be equal to g of x. The argument must be the same. And the third one, if I have log of f of x with the base a is equal to b, you need to write this as its exponential function. You write a to the power of b is equal to f of x. These are the 3 types of methods that we looked at for all those examples that we had earlier. This is one of the application problem. The strength of habit is a function of the number of times the habit is repeated. If n is the number of repetition, and H is the strength of the habit, then according to psychologist C.L. Hall, they're giving us this formula. H is equal to 1,000 times 1 minus e to the power of minus k times n, where k is the constant. They want us to solve for k. So that's all they're asking us to do, is to solve for k for this problem. So we need to isolate k. We're going to use our properties that we learned to do that. The first thing I want to do is divide both sides by 1,000, so I can isolate k. So on the left-hand side, I get h over 1,000 is equal to, now on the right-hand side, 1 minus e to the power of minus kn. The next step is to subtract 1. I'm going to move this 1 to the left-hand side. So I get h over 1,000 minus 1. I'm getting really close to isolating my unknown here. So what we have so far is e to the power of minus kn. I'm going to multiply each term by -1, so I can eliminate this coefficient here. So it would be 1 minus h over 1,000. Now I need to take a natural log of both sides, so I can solve for my unknown. So if the variable that you're solving for appear on the exponents, and when you cannot make the base the same, then you can take a natural log of both sides. You could take a log of both sides also. So we're going to take a natural log of both sides. So as you recall, the left-hand side, if I have natural log of e to the power of x, this whole thing would be equal to x, because the base is the same as e here. So on the left-hand side, this whole thing would be equal to minus kn then, according to this property. Minus kn is equal to natural log of 1 minus h over 1,000. And now we can easily isolate k by dividing both sides by minus n, or multiply both sides by minus 1 over n. And this is it. We isolate k that way. So the key was, at this point, to take a log of both sides, so I can eliminate the e to isolate n. The study monitored a lifespans of 129 robins over a 4 years period. The equation is given to me as y is equal to 2 minus log of 100 minus x over 0.42. Was developed to calculate the number of years y it takes for x% of the robins population to die. How many robins had died after 6 months? So first thing we want to do is let y be equal to 6 months. So it would be 60 divided by 12 would be 0.5 years. And basically we need to solve the equation when y is equal to 0.5. So let's write that down. So y would be 0.5 is equal to this. So basically we're asking to solve for x here. I can isolate x by cross multiplying this. First of all, 0.2 times 0.42, that give me 0.21. If I cross multiply this, it's a proportion. And then what I can do is I can subtract 2 from both sides of the equation, and then multiply both sides by -1, so I can move this coefficient to be positive. Or I can move minus log of 100 minus x to the left-hand side, and then the right-hand side I get 2 minus 0.21. Right at this point here, I need to eliminate the log. So what property I'm going to use here? So let's write it down here. If I have log of x is equal to y with the base b, if I want to eliminate this log, I need to change that to its corresponding exponential function, which would be b to the power of y is equal to x. That's exactly what we're doing here. My base here is 10 when there's no number there. It would be 10 to the power of 1.79 is equal to my argument. There you go. I dropped the log. And then to solve for x, simply isolate x would be 100 minus 10 to the power of 1.79. Just plug the number into your calculator, and that would be your x. About 38% of the robins had died after 6 months.